Good morning and welcome to the next session of the day, Gelfond Schneider Theorem and its proof. Our presenter today is Chamath Hettiarachchi from Northern Virginia Community College. If you have any questions for our speaker during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we will address them at the end of the talk. On that note, I'll hand it over to our first presenter.
Hello, can you hear me, please?
Yes, we can hear you.
Okay, thank you. Okay, so thank you for the opportunity. And so let me start with the theorem. Okay, so how can I share my screen? So
there should be a share screen button at the bottom of your Zoom room screen. Do you see it there?
Yes, I see that. Thank you. Share the screen. Share. Okay, so I'm going to start now, and so this is a theorem. This is Gelfond Schneider Theorem. And if you have two algebraic numbers, alpha and beta, they possibly could be complex, and alpha and is not equal to 0 or 1, then okay, and its beta is irrational, then alpha to the beta is transcendental, which means it is not algebraic. So here's here's a definition of an algebraic number. Algebraic number. Right here. So this is what algebraic number means. Okay. So an algebraic number is a number which is a root of a non-zero polynomial in one variable with integer or equivalently rational coefficients. For example, the golden ratio is an algebraic number because it is the root of the polynomial x squared minus x minus 1. Okay. So that's right. So that means we know all the rationals are algebraic numbers, but some irrationals are algebraic numbers, but not all irrationals are algebraic numbers. For example, pi and e are not algebraic. They are not a polynomial with integer or rational coefficients. Okay. Okay, so let's get back to the theorem now. So this is how we do the prove it. You prove by a contradiction. Okay. So we suppose this is the outline of the proof. We suppose alpha, an algebraic number, and alpha is not equal to 0 and 1. I hope you can see my screen, right?
Yes, we can see your screen. Mm-hmm.
Okay. Is it clear enough?
Yes, sir.
Okay. Thank you. So we pick beta to be an algebraic number such that alpha to the power b is algebraic. Okay, algebraic. Then we are going to show that, okay, beta will be a rational number. Okay, that's how we are going to do it. So we suppose alpha to the power beta is algebraic, then beta becomes rational. We are going to show that. Then by contradiction, we can show that alpha to the beta is not algebraic, which is transcendental. Okay. So this is how we do that. So we only treat a special case, alpha and beta are real numbers and alpha is positive. Okay. And of course, we suppose that exponential beta to ln f is algebraic for real value of ln alpha. And then we know that by properties of algebraic numbers, okay, alpha to the power s1 plus s2 beta is algebraic for all integers s1 and s2. This is by properties of algebraic numbers because they are closed under addition and multiplication. Then what we do is, so we are going to show that we can write this power s1, s2 beta in two different ways. See, it is enough to show that there are two distinct pairs of integers, s1, s2 and s1 prime, s2, for which s1 plus s2 beta is equal to s1 prime plus s2 prime beta. This implies that if you solve this, beta becomes s1 minus s1 prime divided by s2 prime minus s2, which is a rational number. Okay, so then by contradiction, we know that, so beta cannot be rational because we suppose beta is irrational. Then that means alpha to the beta must be transcendental. Okay. So, but before we do that, we are going to use 4 lemmas. We need 4 lemmas to prove the theorem. And the first one is, we have, okay, n polynomials. They are named as a1 through ant, okay, with degrees d1 through dn respectively. And we choose w1 through wn pairwise distinct real numbers. Pairwise means none of them are equal to each other. Okay, that's what pairwise distinct means. Then we create a polynomial called, not the polynomial, so function f of t by multiplying each, okay, e to the wjt, ajt, then adding them, okay, if j goes through 1 through n. This is f of t. Okay, then this is going to be now the lemma says this has at most d1 plus all the way to dn plus n minus 1 real roots, counting multiplicities. That's the first lemma. And the second lemma, I think most of you know that. Okay, this is a maximum value of analytic function. If f of c is an analytic function in the disk, okay, of radius r, open disk for some real number r greater than 0, and if f is also continuous on the closure of the disk, okay, then we know that, okay, f will attain its maximum on the circle, on the boundary. This is, okay, by complex analysis, this theorem. And the second one, the third lemma, let r and r be two real numbers such that, okay, simple r is less than or equal to capital R. And moreover, we have L analytic functions. Okay, each one is analytic in the open circle with radius r and continuous on the closure of the circle with radius r. And then we choose theta 1 up to be theta L be complex numbers such that, okay, each theta 1 is less than or equal to r. Then we calculate the determinant of the matrix, this one. This is going to be L by L matrix. Okay. This is the determinant of this matrix. Then this matrix satisfies this inequality, which is the absolute value of the determinant is less than or equal to capital R or simple R to the power minus L times L minus 1 over 2 L factorial times product of F lambda R, lambda goes to 1 to L. So this is obtained by applying, okay, right here, lemma 2. Applying this lemma, okay, we need to calculate the determinant, and we repeatedly apply lemma to the determinant, then we can get this inequality. Okay, so last one is, okay, last lemma, lemma 4, that's what we need. So we define, okay, delta as determinant of the matrix, L by L matrix, okay, alpha ij, where each alpha j, ij are algebraic numbers. So then suppose that t is a positive integer, positive rational integer. So here we use the word rational because, to distinguish from other integers, there are Gaussian integers, Einstein integers. So this is just a regular integers as we know them, positive integer, for which t times alpha I, alpha j, alpha ij is an algebraic integer for every ij belonging to the set 1, 2 through L. And also suppose that the determinant of this delta is non-zero. That's the determinant of the matrix is non-zero. Then there is a conjugate of delta with absolute value of the conjugate is greater than t to the minus L. So this is what we need, and we will be applying these 4 lemmas in the construction of the proof. So again, we are going to prove by contradiction. So we are going to define or construct a new matrix M the following way. So we choose C. Okay, let C be sufficiently large real number. Okay, we are going to specify this in the due course, how we choose it. And then we take integers L0, L1, S, 3 integers, each one greater than or equal to 2. Then we define L as L0 plus 1 times L1 plus 1. Okay. So now we can find, okay, L0, L1S, okay, such that C times L0, Lns less than is equal to L, C times L1S is less than L, and L is less than a square. But we have an example for choosing, okay, L0 and L1. So if you L is large, you can take L0 as the flow function of S times Lns, and L1 as the flow function of S over 2 Lns. Okay, so when we choose that, your C will be Ln Lns. Okay, this is how we construct the matrix. Okay. So we consider some arrangement of S1 of I, S2I of S squared integer pairs S1, S2. And each S1 goes from 0 to S, is less than S, greater than or equal to 0, S1, less than N. Same thing with the S2, greater than or equal to 0 and less than S. Again, we consider some arrangement of, okay, the integers, pair integers U of J, V of J, for each J going from 1 through L of the integer pairs UV, and U is an integer going from 0 to L0, 0 to L0. We have equal signs here, and V going from 0 to L1. Okay, so those integers are specified. And now we are going to define the matrix. So here's how we define the matrix. So you multiply S1I plus S2I times beta to the power uj, then times alpha to the power S1j plus S1I, S2IB times V to the j. And remember here, this is going to be a S squared times L matrix because we know that. And these SIs, okay, they go from 0 to, okay, we have how many pairs of these SIs? S squared pairs. How many of the UJs and VJs? We have L of them, right? So what we get here is, okay, L squared by S squared by L matrix. This is. So this is how, this is, okay, this is the idea of the proof. Now, this is how we're going to do that. We take any determinant delta of an arbitrary L by L submatrix of M. Anyone will do. Okay, you take that one. Then we use lemma 3 to obtain an upper bound beta 1 for the absolute value of delta. Or we can say an upper bound for ln delta. Because if we have the absolute bound for the delta, then we can take natural log on both sides. Then we can use lemma 4 to motivate that if delta is non-zero, then okay, the absolute value of delta will be greater than B2 for some B2 greater than B1. Then we show that, conclude that delta must be 0 and the rank of n must be less than L. Rank of M must be less than L, right? This is from linear algebra. So take a linear combination of the columns of M to obtain that FT as in lemma 1 with less than L roots, but with, okay, these we have less than L roots, but we have how many roots here? S1is, S2b's, we have L of them. That means since this must be less, that means some of them must be equal to each other, at least two of them. Because we have L roots, then we conclude that, okay, that means then we can show that, okay, beta will be rational. So let's start now, okay. So we are going to find an upper bound for delta, absolute value of delta, okay, which is a determinant of the matrix, L by L matrix we just, okay, defined. So we have not specified the arrangements defining S1 of I, S2 of I, and V, U of J and V of J. Okay, so now we are going to define them. So we are going to define the delta as determinant of Fj zeta I, where this is how Fj of Z is defined as Fj of Z is defined as Z to the Uj alpha to the power Vj Z, and here Ij goes from 1 to L, and zeta I is going to be S1 I plus S2 beta, and I goes from 1 to L. Okay, now we see that Uj is a non-negative integer for each j, Uj, right here Uj, non-negative integer, because we said, okay, Uj non-negative because Uj is going to be between 0 and L0. So it's non-negative integer. Okay, then we can write alpha to the power Vj times Z as okay, exponent of Vj times Z ln alpha, where ln alpha denotes the real value of the logarithm. Okay, so we know that because of that, Fjc is uniquely defined. It is uniquely defined. Okay, it's a single valued function. So then we know that Fjc represents an entire function for j, for each j. It's entire, right? We know that this is entire, exponential functions are entire. So the product of two entire functions will be entire. So that's one. So now, okay. Also, we have this inequality. The absolute value of e to the power z1 c2 is equal to e to the power real value of c1 c2. I think this is from what? Euler's formula? Yes. So less than or equal to e to the power absolute value of c1 c2. That's equal to e to the power absolute value of c1 times c2 for all complex numbers c1 and z2. Right? We know that. So we are going to apply this inequality to this one, get the upper bound. Okay. So then we can write, hence for any r greater than 0, fjr will be less than, okay, u r of uj e to the power vj r ln alpha, by applying this, because we know our zeta 1 and zeta 2 right here, right? Exactly. And right, we have alpha, we have exponent here, alpha, and then we have s this one. So we can apply it by writing, okay, the product f of c as e to the power 2 complex numbers c1 and z2. So we can apply it. By applying, we can get it, this one. So that means if fjr is Okay. Yes. It will reach ln alpha. Let me check something here. Okay. Yes. I think we get it from here. Yes. Lemma. Yes, you had to apply lemma 2 and lemma, yes, lemma 3, lemma, yes, this one, yes, exactly. Lemma 2. Okay. Sorry. This one. Okay, then we are going to use lemma 3. We get this from lemma 2, yes. We are going to apply lemma 3 with R is equal to, we specify the values for R now. R will be S times 1 plus absolute value of beta, and capital R will be E squared R. Then therefore some constant C1 we can obtain that, okay, L1 alpha is going to be greater than, less than or equal to. That means we apply this one right here. We apply lemma 3 now. We apply lemma 3. Lemma 3 by taking, okay, ln on both sides. By applying lemma 3. This is lemma 3, okay, on both sides. So we get this inequality right here. This one, ln of absolute value of delta is less than or equal to L minus L1 plus ln of factorial L plus L times maximum of these ln of fjr, these fjrs, ln of fjrs going from j got from 1 through L. Okay, so this is the same as above. This one minus ln minus 1, and this is will be ln L because factorial L ln L, right? Because by factorial we can get the yes, you're adding ln 1, ln 2, ln 3 all the way to ln L, which is less than L times ln L plus L, okay, L0 ln R, LR ln alpha. Okay, from this one, you know the okay, ln of you take ln of this side, each fj of R, and then you get this one. So you have L of them, so you get L1 RLN. So then what we can do is you can multiply this one, you can multiply L by minus L, get minus L squared, and then you get expression here. Okay, the expression will be plus L ln L, L0 ln R, L1 R ln alpha. What you can do is you can write this is less than some constant C1 times L0 ln S plus L1 S. This 0 is an arbitrary constant. We choose it to be, okay, big enough so that the inequality will hold. And most important thing here is this C2 is independent of C. It is independent of C, the value C. Okay, so we choose C here, right here. This is how we choose C. And our C was ln ln S. That's our C. And this value C2 is independent of C. That's very important. Okay. The independence. So because of that, so we can choose C sufficiently large. That means we can choose C to be greater than or equal to 4C1 and then plug it in here. And then we can, okay, reduce this to ln of determinant of delta will be less than or equal to minus L squared over 2. So we get the first upper bound. So sorry, first we get the upper bound. And the next one is the most complicated thing, the lower bound. Okay. So I'll try my best to explain it. Okay. So lower bound. So to get the lower bound, in case delta is non-zero, we use lemma 4. Okay. So this is how we do it. And suppose that t prime is a positive rational integer for which t1 alpha, t1 beta, and t prime alpha, t prime beta, and t prime alpha beta are all algebraic integers. Okay, these are all algebraic integers, and here's the definition of algebraic integers. give the definition. Okay. This is algebraic integer. So in algebraic theory, an algebraic integer is a complex number which is which is integral over the integers. Okay, I don't know whether you can see this, right? Let me just, yes, make it bigger. Okay, so this is what algebraic means. This is algebraic integer. So in algebraic number theory, an algebraic integer is a complex number which is integral over the integers. That is, an algebraic integer is a complex root of some monic polynomial. A monic polynomial means a polynomial with leading coefficient 1 and whose coefficients are integers. Okay, so the set of all algebraic integers is closed under addition, subtraction, and multiplication, and therefore is a commutative subring of the complex numbers. Same with like algebraic numbers, algebraic integers are closed under addition, subtraction, and multiplication. Okay. So let's get back to the theorem. Okay. So we have here, yes, each t prime alpha, t prime beta, t prime times alpha to the beta, all algebraic integers. Okay, then we create another number called t by raising t prime to the power L0 to SL1. Okay, remember this is again algebraic. Okay, why? We know that by properties of algebraic integers. Okay, but this is going to be algebraic integer again. By properties, we saw that algebraic integers are closed under multiplication. So it's going to be algebraic. Has the property that t times any element of M, and hence t times any element of the matrix defining delta is an algebraic integer. Okay. So this is now we can apply lemma 4. So let me go back to lemma 4. And this is what the lemma 4 is all about right here. Sorry. Right here. So you have a determinant consisting of all algebraic numbers. And if you have a t as a positive integer for which t alpha I alpha j is an algebraic integer for every ij belonging to the set 1, 2 through L, then if it is determinant is non-zero, then you can say there is a conjugate of delta with absolute value of greater than or equal to 2 to the minus L. Okay, conjugate of delta. And by the way, a conjugate means if you have the question about the conjugate, this is what conjugate means. Conjugate this is in field theory. In mathematics, in particular field theory, the conjugate elements of algebraic conjugates of an algebraic element alpha over the field extension L over K are the roots of the minimal polynomial pk alpha x of alpha over K. Okay. That means it's going to be, okay, this is roots of, if we take roots of the minimal polynomial for alpha, all the roots are going to be conjugates. So alpha itself is a conjugate. Okay. So now we can apply lemma. So that means there is a conjugate of delta with, okay, its absolute value greater than or equal to t to the minus L. Okay, so we're going to apply it now, lemma right here. Okay, so that's one. So this is, therefore by lemma 4, if the determinant is non-zero, there's a conjugate of delta with absolute value t to the minus L, and t to the, so t is going to be t prime L1, you multiply it by L0 plus 2s L1. This is what you get. Okay, So then we can show that it will be shown later. We are going to show it later. Okay. If delta is non-zero, then there is indeed a constant C2 again independent of C, for which ln of delta, absolute value of delta will be greater than or equal to minus C2 times L0 lns plus SLL1. We're going to show that. Now we are going to show that. Now conclusion, we are pretty close. All you have to do is establish this inequality. Okay, so before that, let's see. Now, if you suppose both two inequalities are true, then we are going to get a contradiction. Okay, this one. So we see that for C sufficiently large, if C is greater than or equal to 8C2, okay, our upper bound ln of absolute value of delta would contradict A. Okay, if I choose C to greater than this, so we get a contradiction, which means that delta must be 0. It's simple calculation, and then delta must be 0. That means the determinant of the matrix, column, that means since we get that the column must be linearly dependent. Okay, since this is from linear algebra and determinant must be since determinant is 0, that means the column must be linearly dependent over the real numbers. In other words, that means we can find there exist real numbers bj, not all of them 0, such that bj times fj zeta I, j goes from 1 to L, will be 0 for each I 1 through L. Okay. Now we are going to what we do right now is we are going to write this in a special way as a double summation using the double summation notation. And to do that, we have to remember these are ordered pairs. Remember, ordered pairs do not have a natural order like the real numbers. And we have to create an order for these numbers. You go to order them. I think we are using the dictionary order. Yes. So we ask u in such a way that, so we say that uv will be less than or equal to u prime v prime if and only if v is less than v prime. Or if v and v prime are both same, then uv will be less than or equal to u prime v prime if u is less than or equal to u prime. So this is dictionary order. Okay. Now what we can do is we can write this as a double summation. Remember, we have L here. J goes from 1 to L. Remember, L was defined as L0 plus 1 times L plus 1 right here. This is how we define L. Way back. Okay, right here. This is your L. Okay. That means we can write this using double summation the following way. Okay. So that means if you calculate this, BJs, you can replace J by L0 plus 1V plus U plus 1. This is subscript. Then zeta to the power U, alpha to the power V zeta I. And here U goes from 0 to L0, V goes from 0 to L1. For each I going from 1 through L. You can do that for each I. Okay, now we are going to write this double summation in a special way. That means we take the first summation inside, we can replace that by this one. We call a function AV of t. So we can write it, this first summation as, AVT, sorry, not AVT, I'm sorry. That's not right, yes. We write this one as, yes, we can write this as AVT, V goes from 0 to L1, e to the W subscript VT, where this is my AVT. So AVT will be multiplying all the numbers. So U goes from 0 to L1, BL01 times V plus U plus 1 times, and this is going to be, this rest will be T to the U and T to the U, and here WV is VLN alpha. VLN alpha, which will produce this one, alpha to the power, this one, yes. And then your T will be zeta I, which is going to be S1I plus S2I beta. So we define AVT, okay, and T, okay, by rewriting this double summation as sigma we got from 0 to L1, AV of T e to the WVT. Okay. So we know that if you apply lemma 1, what we have is, okay, this function right here. If you go to lemma 1, what you have here is, this is lemma 1, all the way here, lemma 1, right here. If you have A1 through A and T, okay, non-zero polynomials in RT, okay, having degrees D1 to Dn respectively, if W1 through Wn be positive distinct real numbers, pairwise distinct real numbers, then this function f of t has at most d1 plus dn plus n minus 1 real roots. We applied that one because we have exactly the same function created down here. Okay, exactly this one. So okay, so we apply by lemma 1 for some bj not equal to 0. Okay, some bj not equal to 0. It is from lemma 1 that there are at most L0 times L1 plus 1 plus L1 plus minus L, which is, by the way, less than L, distinct real roots. Okay, so these are the degrees adding. Okay, this is going to be the degree at n here minus 1. Okay. Yeah, then. And now we know where the problem is now. So it has less than L distinct roots. But what I have here? How many roots we have here? We have L roots. But their lemma says, no, you cannot have only roots less than L, number of roots less than L. What happens? That means two of the roots must be the same. The two of the roots must be the same right here. Okay, so these are the roots and two of them must be for some I and I prime, they must be the same, which will show that beta will be, remember, S1I, S2I, S1I prime, S2I are all integers, non-negative integers, which means, so beta is going to be, okay, a rational number. And not only that, these are necessarily distinct. That means we never divide by 0. Okay, they are okay, necessarily distinct. So that means, because that's now when you solve this one, you get beta as a quotient of two integers, which is rational. So we can call that B says rational complete in the proof. Now all we have to do is show this inequality because everything depends on now this inequality. Okay, lower bound. Okay. So this is the proof of inequality. We call it inequality A. Yes, right here. This is the one. So once you prove that, we are done. Okay, to finish the proof, all we need to do is to show that if the delta is 0, then the inequality A holds. So we suppose that delta is not equal to 0. And recall that TL alpha is an algebraic integer. It's an algebraic integer where T is going to be T prime to the L1 plus 2 L1, L0 plus 2 SL1. And T prime is a positive integer, depending only alpha, beta, and alpha to the beta. They only depend on these three values. Alpha, beta, alpha to the beta. Okay, so this is algebraic. And again, we know that okay, for an algebraic number, we define a norm, new norm called, okay, I call norm W. for the algebraic number, okay, we denote non-W by the maximum of the absolute value of a conjugate of W. Okay, remember, conjugate means roots of the minimal polynomial of W. So that means you take all the roots and you take the maximum of those roots. We call it norm W. And we can show that if you add W plus W prime, the norm of W plus W prime will be W norm plus W prime norm times. And yes, that's first inequality. Second inequality, the norm of W times W prime will be less than norm of W times W prime. And then again, there's another one, equality. The norm of alpha times W will be absolute value of alpha times norm, where whenever W1 algebraic numbers and lambda belongs to Q, rational numbers.
I apologize for interrupting, but I want to give
Yes.
a quick 10-minute notice to allow time for questions.
Okay, I'm almost done, yes. So these are going to be, okay, algebraic numbers. So this one, so we obtain that. This is going to be, okay, this is going to be the norm of TL alpha. Okay, we can pull TL out. And then what we do here is we apply this right here, TL delta. So delta, we apply this one. Yes, this inequality. Okay, delta. Okay, so we apply this, we get the inequality to this one, delta, and we apply this one repeatedly. These inequalities, these two inequalities and the equality here. Okay, we apply them. We get this one by repeatedly applying. We have that T alpha delta is an algebraic integer in Q, alpha beta alpha to the beta. And we can deduce that, okay, remember this is by definition of a mark, okay. Yes, of a algebraic number is an algebraic integer, then we can say that TL delta is a root of an irreducible monic polynomial of g of x degree n, where n is the product of the degrees of the minimal polynomials for alpha, beta, and alpha to the beta. Okay, now we know that each root of gx is a conjugate of TL alpha. That's right, by definition of conjugates. Then the product of all the roots of gx has absolute value greater than or equal to 1. And each root of gx has absolute value less than TL delta. Then we apply these two inequalities. We get here TL alpha, absolute value, TL delta alpha value will be greater than or equal to absolute value of g of 0, then norm of T to the L delta to the power n minus 1. And then, okay, we apply this inequality here. Remember, we obtain this one for delta T, norm of TL delta here. We apply it and we get this inequality. This one, by applying it. Okay, you're raising that to power n minus 1. Okay, this is 1 over TL delta norm. Then we take the, okay, ln on both sides. Right? So now we can write this one as, okay, these numbers, recall that these numbers and T prime n are all constants depending on the alpha and beta. They do not depend on C. Okay, so we can write this inequality as, like in the case of the upper bound, you can write the lower bound, okay, like this, the lower bound this way. That means, okay, so the C2 does not depend on C. So that means we got the inequality. Okay, then the proof follows. Okay. So any questions?
Hi, everyone. If you have any questions, please do not hesitate to put them down in the chat box at the bottom of the Zoom room screen. Well, it looks like we don't have any questions. Well, thank you so much, Professor.
Okay, thank you for,
Hettiarachchi.
yes.
Yes. Thank you for all the valuable information you shared with us today. If you have remaining questions, feel free to stop by the Hawks virtual booth to speak with a member of our Hawks team. The next session will begin at 2 p.m. Eastern. You can view the chat for the session meeting room links, or you can access them via the conference website for a complete list of the sessions and their descriptions. While accessing the conference website, don't forget to swing by the virtual booth to say hello to the Hawks team, view a quick 5-minute demonstration, and be entered to win a $50 Amazon gift card. We'll see you at the next session.
Okay, bye.
Thank you. Have a great day, Dr. Hettiarachchi.
You too.